Okay, let's continue. So in the last class we were looking at band gap reference, how to generate a good voltage reference, and in particular we looked at how to generate voltages that are fractions of the band gap voltage, that's the fractional band gap. And towards the end we also saw how we can get a simpler circuit without using an op-amp, although it is not that efficient compared to the one with op-amp. This also reasonably works. And here interestingly this has both positive and negative feedback, or I would say there is a strong positive feedback here, but the idea is as long as the loop gain of the positive feedback loop is less than 1, we are okay. And another way to look at the same scenario is this: you have a negative feedback because of this loop, sorry, positive feedback because of this loop, but you also have a strong negative feedback because of this source regeneration structure. So the idea is you make the source regeneration stronger. So generally if you have two impedances, let us say Z1, Z2, and if Z1 is greater than Z2, you put the larger impedance on the source side so that provides a stronger source regeneration. Okay, that's the whole idea. And sometimes this structure is sometimes referred to as the floating mirror. Again, this essentially keeps the current in the two branches to be equal, at the same time ensures that the node voltages here are also equal. Sometimes this is some jargon you might find sometimes, but yeah. And of course this is the final circuit we had. What is it? Yeah, this is the final circuit we had, and of course this is not complete. Let's just complete it and move on. So this is the thing, and here if this works correctly, these two voltages will be equal. So this is VEB1. So the current flowing through this will be the PTAT current because the current is a difference between the VEBs by R. You can also get a CTAT current by putting another resistor here if you want. So this will draw a CTAT current. So here you will have sum of the two currents. So now you can essentially do the same. You can take it, mirror it, pass it through another resistor and sort of get the voltage. Whatever we did with the existing old band gap circuits with the op-amps, the same you can do here. So which means now you need to add the same resistor here. But I hope you get the idea, right? That's all. Cool. So now, so couple of minor points with respect to band gap. So let me just go to the circuit with op-amp. I'll take this one. Yeah, I'll take this. Okay, so here as we know, the output in any band gap we get as CTAT voltage, which is one diode drop plus some gain times a PTAT voltage, which is the delta VEB, and in this case the delta VEB, if you recollect, this will be VT times natural log of n. So you typically choose this Kp and VT, ln n, so that the slope sort of cancels. So if I take the derivative of V out with respect to temperature, it is 0. That's the idea. Right? So now, this n is essentially the number of diodes that you are putting in parallel. There is technically no restrictions. It can be any integer, but in practice we choose it to be of the form k square minus 1. That is a perfect square minus 1. Reason is simple. Let us say you have n diodes here, one diode. You need to have total of n plus 1 diodes. So let us say you have n plus 1 diodes, you put it like this. Let's say put it in one straight line, versus let us say you put it in a 2D array like this. Which of them do you think will be better with respect to mismatch? Why? Yeah, the idea is as two elements are spaced farther and farther apart, you expect that there is going to be mismatch. Again, mismatch is coming because in the fabrication process, the steps happening and in this exact physical location might be different from what is happening on another location. So closer the location is, you are guaranteed to be more matched. So it is more beneficial to keep it in an array like this. And because of this reason, if you keep it like a perfect square, where the total number of elements is k square, that is good. So typically we choose the n to be 8 or 15 or something. That's all. And another fine point with respect to band gap is this. So let us say now you don't know anything about the circuit. Okay, I just gave you the circuit and you are trying to solve for it. So let us say this is the current I1. Let us say the current I1 is essentially, this voltage is VEB1. It is VEB1 minus VEB2 by R1, and the diode voltage, remember, it is Vt times natural log of the current plus 1. Similarly, if I look at VEB2, now here I have n diodes. Through all the n diodes, the current flowing is I1. So what is the current flowing through one diode? I1 by n. So my VEB2 is essentially Vt times natural log of I1 by n Of course, see, if you know that diode is sufficiently forward biased, then you can say that this term is greater than 1, you can ignore 1. That is okay, but let us say you don't know anything, you are trying to solve from scratch. You might do it like this. So this is essentially Vt times ln of 1 plus I1 by Is by 1 plus I1 by n times Is by R, right? Now this is the equation you will try to solve. By looking at this equation, can you tell me if there is a trivial solution that might satisfy this? Without solving it, but just by looking at it, is there a value of I1 that will immediately satisfy this equation? 0. If I put I1 to be 0, natural log of 1 is 0, this is 0, it's completely satisfied. So it turns out this all 0 solution is an equally valid solution for this circuit. So what that means is, if you don't take care of things properly, the circuit might settle to an operating point where the currents here are all 0. So the voltages here will be 0 and the circuit is dead. But luckily it turns out this is not a really stable operating point as such, because let us say the circuit is dead, so this voltage is 0, for example. In practice there is going to be some kind of noise from all kinds of elements. So anytime a noise current is getting injected into this node voltage will try to increase, then the diode will start to draw current, and then this sort of kicks in and starts to work. So this is what we call as a metastable operating point. Just like you might have heard metastability in digital circuits, right? Same thing. That is a metastable point. That means it is not really stable. Any disturbances you will see around that metastable point will push it to the final required operating point. And the classic analogy is, you try to, this is like trying to balance a ball at the edge of a cliff. Even if there is someone goes into to the ball, it will just same. But although this is not really a stable operating point, in practice you don't trust the noise in the circuit to sort of get you out of this metastability. We typically have special or dedicated small circuitry that kind of detects if your circuit is in metastable operating point and brings it back. And that can be any, there are multiple different variations. I'll give a couple of them in your assignment to understand. The idea is you need to sense if your circuit is in metastable operating point, that is if voltages are 0. If the voltages are 0, you start to push in some current so that the circuit starts to work. But once the circuit starts to work, the circuit should stop responding, right? Something like you sense if this voltage is very small, you push in a current, but as the voltage increases, this should stop pushing in current. You can think of, there are multiple different things, and these are called startup circuits. I'll give a couple of them as example in your assignment, so that in your practice set, so that you understand what kind of circuits they are. They can be 1 or 2 transistors, nothing complicated. Sometimes even a single transistor is sufficient. You can have 2 transistors, or it's pretty simple. Okay, cool. So that's majorly about band gap reference. So now you guys know how to design an on-chip voltage reference. So you can get a reference voltage Vref. And remember, our goal is to make sure that we are able to provide DC supply to rest of your circuits. Right? So now let us say you try to, let's say this actually Vref is equal to your VDD of one of your chip. Now let us say you try to go and connect it to your circuit like this. Your circuit will draw a lot of current. So which means the band gap reference might not be able to provide. So in a way, this is loading the circuit. So to avoid loading, what we should do? Should put a buffer. How do you make a buffer? Yeah, component. But now you guys know how to make op amp. Can you make better buffers with op amp now? The unity gain configuration. So what we do is this. So you take VREF, you connect it in a unity feedback configuration. Now the output, if I call this as VDD out, that will be equal to your VREF. So now you can go and connect your actual circuit. Now your circuit will draw a lot of current, but who will provide this current now? The op amp will provide, because remember there is going to be an input supply VDD. So the current will basically be drawn from the supply. Again, the nice thing is this supply, even if it's not really constant, it is okay, because from the op amp all you need is the following. You want it to have a large DC gain. As long as the DC gain is sufficiently large, you're okay. Whether the DC gain is 1000, 1200, 1500, it's okay. So that's the nice thing with feedback. Okay, so this works, but let me take it to next page. Okay, so this works, but one minor issue in practice. So once again, now this is an op amp which takes in 2 inputs, 1 output. You will realize it using a 5T OTA. But again, the moment your circuit here starts to draw a lot of current, when it draws a lot of current, it is as though you are connecting a small resistive load to the output, correct? So now if you have a single stage op amp, you already know that we can't connect a small resistive load. So what do you suggest we should do? Should have at least one more stage for driving it, and that's what is commonly done. So what is done is this. Let us say let this be the first stage. You put a PMOS transistor, let us say. Now this will be your output. Let's say you have something here, your actual, you can put your circuit here that draws the current, and you can actually close the feedback. And of course this will also be powered by the input VDD. So earlier my signs of the feedback were, signs of the op amp was this. Now I have added one more PMOS stage at the output. So what do you think will happen to the signs? They'll flip, because you have one more inversion due to this PMOS. So I'll directly flip it. So of course if you do this, I have again my VDD out to be equal to VREF. And typically, instead of drawing something random like this for the circuit, we usually replace it with a current source, with the understanding that this current source essentially models the current drawn by your final circuit. That's just a convenient way to model. So now let us say this works, but let us say you want your output not to be equal to VREF, but let us say K times VREF. So what would you change in the circuit now? The feedback factor should not be unity now. The feedback factor should be what? If let us say I want the output to be K times the reference voltage VREF, what should feedback factor should be? 1 by K, right? So, and how do you realize the feedback thing now? A resistor. So let me make hold on. So what will it will look like this now? I have, okay, sorry, let this be there. Yeah, so let us say I have a resistive divider like this. Same thing, instead of connecting the output directly, now I am feeding a fraction of the output. and the feedback factor should be 1 by k. So this should be k minus 1 times some R1. This should be R1. Is that okay? So this forms the basis of what we call as linear voltage regulator, or often called as low dropout regulator. And this is abbreviated as LDO. Now this is called linear regulator because if you actually try to calculate the power efficiency of this circuit, efficiency is nothing but you see how much is the power you are actually delivering it to your load versus how much is the total power you are drawing from your DC supply. So here what is the power I am delivering to the load in terms of VDDs and currents? Yeah, K times Vref times I load, or I will say VDD out times I load, right? So that the power I am finally delivering is VDD out times I load. Now if I find the power that I am drawing from in the entire circuit, now I am drawing current from the supply VDD in. So that current comprises of the current in this PMOS transistor and the current in the op amp. Now current in the PMOS transistor is this current plus the load current. Typically the current that you will be driving to the load will be significantly higher than whatever current you are drawing here. This current can be in the orders of few tens of milliamps, hundreds of milliamps, or even few amps depending on the circuit. So this current is typically significantly larger than what you have here, because you can have a very large R1 so that the current is small. If that is the case, what is the current flowing through this transistor approximately? This is I load approximately, right? Same this similarly even the current drawn in this op amp can be kept really small compared to the load current. So the very optimistic power drawn from the input is VDD in times I load. Again, this is a very optimistic calculation because in practice you will draw slightly more current than I load from the supply VDD. Slightly higher but approximately. So now you clearly see the efficiencies ratios of the input and the output and the output and the input. So efficiency is linearly proportional to the output voltage, so it's called linear regulator, and it's called low dropout regulator because this particular configuration is used only when the drop between the input VDD and the output VDD is very small. For example, in the order of 100 or 200 millivolts, or maybe 300 millivolts, depending on. And why do you think we want to keep the dropout between these 2 points to be really small? Yeah, the point is, it cannot be greater, but what I'm saying is, typically it is used for cases where my VDD out is, let us say, 100 to 300 millivolts smaller than VDD in. Question is, what if it's, let us say, 900 millivolts smaller than VDD in? Why can't you use it that way? Yeah, as you see, efficiency depends on this ratio. If you want a very good efficiency, you better keep my VDD out to be as close to VDD in as possible. That's all. So because of this reason, you keep the dropout voltage to be as small as possible. So although LDO implementation at the heart of it is essentially like a two-stage op amp, there are fine nuances in the actual implementation. One is the following. As I already mentioned, the load current here can be significantly large depending on the circuit that you are driving. Let's say the current is of the order of several hundreds of milliamps or sometimes even few amps. Then we don't use a normal PMOS here because normal PMOS cannot handle such high currents. So we tend to use a particular kind of MOSFETs called power MOSFETs, which are rated to handle large current. Okay. That is just one minor thing. And other point is, although this is like a two-stage op amp, The actual considerations in this circuit is slightly different, that's all, right? And we'll briefly look at some of those considerations. Now look at the circuit. So here we have a negative feedback loop. This negative feedback loop, what kind of control source it is trying to make? By voltage control current source. No, is my circuit trying to keep I load constant, or what is it trying to keep constant? It is trying to keep my VDD out to be exactly K times Vref. Correct? So what kind of control source is this? Voltage control voltage source. So which means if I try to find the output impedance of this circuit, do you think it will be really small or really large? Really small, because output is a voltage source. So let's actually calculate and see. So I'll remove the load for that. So again, this is all small signal calculations. So let us say this is my output impedance. Okay. Let us say the first stage has a gain of A1. Now by inspection, can you tell me what this R out quickly? Will you be able to tell? Okay, but do you think this is small or large? Seems about right. So let's quickly calculate it. This is roughly correct. So let's say apply a test voltage V test. How much of this V test will appear here? Let's say beta. Let's figure the feedback factor beta times V test. What will be this voltage? Again, this is all small signal calculations. So let me remind you, this is all small signal calculation. So this is ground. So what will be the gate voltage of the PMOS here? Beta times A1 times V test. Now because of the gate to source voltage of the PMOS transistor, what will be the current that we are drawing? GMP times plus, of course, you also have currents flowing through the R0 of this transistor and this resistor. So my I test will be V test by the total resistor K times R1 . So if you calculate this, is it correct? Yeah. So if we simplify this, what do you get? Let me write it this way. It is R0P parallel K times R1 by 1 plus beta times A1 times GMP into okay. I mean, whatever you told is correct. I have just written here. Is that okay? I have considered this to be a single resistor and sort of took LCM and put. And particularly here, what is this term? Beta times A1 times GM times R. Overall gain, can you be more specific? It is essentially the loop gain of this feedback loop. Let us say I break the feedback loop. I break it at the gate here, input here. If you apply any voltage here, A1 times voltage appears, and A1 times the gain of this stage will be the thing that appears here, times beta will return back here. Is that okay? So if I apply a test voltage, let us say I apply some Vi, A1 times Vi comes here. The voltage here will be A1 times Vi times the GMP times R0P parallel K times R1, and here will be beta times this entire thing, A1 times GMP times. So this is essentially the loop gate. So I can write my output impedance, output resistance this way. So let me see if I can make some space. So my R out is essentially this value. I will not write it as of now, by 1 plus loop. And if I look at the numerator, it is R0 of the PMOS parallel to K times R1. that is essentially the output impedance when the loop is broken. Right? Because when the loop is broken, this voltage doesn't change, this is incrementally short, correct? This is incrementally short. So the output impedance is R0 of the PMOS parallel to K times R1. So in a way I can write that the output impedance in closed loop is the output impedance in my open loop by 1 plus loop gain. And this is true if your negative feedback loop is trying to mimic a voltage controlled voltage source. If you have a voltage controlled voltage source, the output resistance or output impedance in the closed loop will be the open loop output impedance by 1 plus loop gain. Of course, now this we can further approximate. This term, if you approximate further, assuming loop gain is really large. So what does this approximately equal to? If I say that loop gain is really large, so these two cancel. So you end up with 1 by beta times A1 times Gn. So now let's see, erase all this. Okay, so let's see. So this is your approximate output impedance. So this is again assuming that there is no capacitors in the circuit. Now let's assume that the op amp has one pole. So maybe I'll model it this way. I'll say that this is a GM, has some R, let us say some R1, which is not R1, maybe RO. Okay. Let us say it is some GM. So GM times RO was your earlier gain A1. Now let us say you also have a pole. So earlier my A1 was GM times R1, R0. Now let us say you also have a pole due to a capacitor here. Let's call it C1. So now my transfer function is no longer A1, it is A1 of S. A1 of S is A1 by 1 plus S by P1. Okay. So in that case, if I repeat this calculation of output impedance, what do you think I'll get? I mean, when the gain was just A1, the output impedance was 1 by beta A1 GM. Now the gain is not constant, it is A1 of S. So if I find Z out of S, how will it look like? Huh? Same thing, A1 gets replaced by A1 of S, that's all. Right, and if I expand it, so we have 1 plus S by P1 in the numerator, correct? Now if you have to model this output impedance using simple electrical equivalent, what are the circuit elements you will need? A resistor and an inductor in series, right? So which means it seems like the output impedance has an inductive component, correct? Now two questions. Why does it make sense that I have an inductive component in the output impedance? And second question, have we seen this kind of behavior somewhere else in the circuit, I mean in the course before? Huh? Where did you see? Director. No, guidator is something different. Guidator is where you try to mimic an inductor using GMs. But now it seems like if I look at the output impedance of some circuit that has an inductive component. Okay, first of all, why is there inductive behavior in the impedance? Yeah, remember that anytime I have a voltage controlled voltage source, and if you have a delay in that feedback loop, we expect that there is going to be an inductive component, right? Yeah, this we saw, as he told, this we saw in common mode feedback. So this should not be surprising, because let us say you try to find the impedance here. Let us say you apply some test current, let us say for example. Now if the capacitor is not there, let me remove the cap. If the capacitor is not there, anytime you inject any current here, that change is instantaneously fed back, correct? So anytime you find any change in any of the points in the feedback loop will respond instantaneously and make sure that the gate voltage here is increased or decreased in the appropriate manner, so that the output voltage doesn't change so much. Because the goal of the feedback loop is to keep this output to be equal to a constant. So any small signal change should be completely suppressed. And if there is no cap, let's say you inject a current, the change is instantaneously fed back. The gate voltage will increase or decrease to keep this voltage constant. So that's why at DC, if you calculate the output impedance, this is very small. But now let us say you consider a cap. Now I inject let us say some step current or some current at the output. At t equal to 0 plus, what can you say about the capacitor? Approximately how do you treat it as? At t equal to 0 plus, you can treat it as a short circuit. So which means now you see that the gate voltage is incrementally ground, source voltage is ground. It is as though the feedback is not active. So at t equal to 0 plus, at that point if I look at the output impedance, what will that be? KR1 and something else? Parallel with R0 of the PMOS. So at t equal to 0 plus, I see that output impedance is K times R1 parallel R0 of the PMOS. And even when I say t equal to 0 plus, I am looking at small frequencies or really large frequencies. So at large frequencies, my output impedance is really large, and at DC it's very small, so you have an inductive here. And in fact, this is the way the loop here operates. The loop is trying to keep the output voltage constant. So anytime there is any change in any point, let us say here, anywhere, the loop is trying to keep this voltage constant by immediately trying to change the gate voltage of the PMOS, because this is what is finally determining this voltage. And in fact, you can also interpret this circuit in a different way. So, but before that, this point is clear. We have an inductive output impedance. Okay. So let us say I know that I have to drive a current I load to my actual circuit. This is my actual circuit demanding a current I load. And my job is to ensure that I am able to provide this current exactly, and at the same time I keep this voltage to be some VDD out. Correct? Now let us say I have a current source with the value I load. I can go and connect it. That will make sure that this is able to provide the current here. But I also want to generate an output voltage. To get an output voltage, I have a current. How can I convert this current to voltage? Pass it through a resistor. I can put a resistor here. But as of now, what is the current flowing through the resistor? 0. So if I want to have the voltage to be VDD out, what should I do to the current? Yeah, let's say this some R. I should have some other current, let us say I2. If I have this setup, idealistically it will work. Fine. But unfortunately, you do not know exactly what will be the load current, because it can change. Or even if you exactly know, it is not possible for you to have a fixed current source of that value. So now this can no longer be a fixed current source. What should this be now? It should be a variable current source, and you vary this current based on what now? Yeah, load current, but you can't sense a load current. What can you sense here? You sense VDD out, correct? Because if let us say this current is not matching I load, then this VDD out will increase, decrease, blah blah blah, right? So that's what you do. You make this a voltage controlled current source. You sort of take the output, or let us say take fraction of the output, compare with an op amp, and pick it. And that's another way to interpret the same circuit. So anyways, let's continue. So here we have sort of not considered one important consideration. We have overlooked it so far. See, this is a two-stage op amp. So for this to work properly, what should I do? Should do compensation. What kind of compensation we can do? Yeah, Miller. So that is one straightforward thing. You can put a Miller cap here. And sometimes in LDOs, what is also done is the following. See, in Miller compensation, the idea is you put this cap. This sort of behaves like a larger cap at low frequencies here. So the effectively you have put a large cap here, correct? So instead, sometimes people also try to put an explicitly large cap at this node, or sometimes a very large cap at this node, so that the pole at this node or this node moves to a very low frequencies, and that is also fine. I mean, essentially there are three things you can do. You can do Miller compensation by putting one capacitor, or you go and put a very large capacitor at this node, or you go and put a very large capacitor at this node. All three of them will sufficiently work, or will work, and all three of them are commonly used. Again, each will have its own pros and cons. So maybe we'll briefly look at what might be the considerations in putting a large capacitor at the gate or at the output. Now remember, this is a negative feedback loop trying to keep this voltage to be constant. So one important spec here is the output impedance, right? Because you want the output impedance to be as small as possible. So let's qualitatively see how will the output impedance look like when I, let us say, have C1 as the dominant cap. Let us say C1 is much greater than C0. So let's intuitively try to sketch the impedance, output impedance. This is frequency, this is Z out. I am plotting in, let's say, dB. Now at low frequencies, capacitors are open. We already computed what is the output impedance. So that was some very small value, 1 by beta times A1 times GMP. At DC it's very small, expected. Now I keep increasing frequencies. My C1 is much greater than C0 because I put a very large capacitor here to compensate it. So if I keep increasing frequency, what will happen first? I mean, at DC both capacitors were open. Now I'm repeating this experiment by increasing the frequency slowly. So what will happen first? Yeah, I mean, C1 is greater than C0. So which capacitor will start to deviate from open circuit behavior? C1. So after some point, C1, let us say it's completely short. Now if C1 is completely short, what is the output impedance now? Yeah, we already computed. This is R0 of the PMOS parallel to KR1, and that's a large number, so somewhere here. So you'll essentially get something like this. Again, an inductive behavior, we already knew this, correct? And interestingly, tell me this. So to find the output impedance, essentially, let us say I inject a test current. I find the voltage. That's the experiment I'm doing, right? For finding the output impedance. So in this case, I see that my capacitor C1 is shorted, but my output is not 0, right? I'm applying an input current and trying to find the output voltage, correct? But when I short one of the capacitors, the output is not 0. So what can you infer from that? There is a 0 in the circuit, and that you can clearly see, right? Because of the 0 is where you have an increasing pole. So in a way, this capacitor C1, it contributes to a 0 as well as to a pole. I mean, that's why it increases and then sort of flattens. Make sense? Okay, so now let's continue the experiment. I keep increasing the frequency further. Now what will happen after very large frequencies? C0 will act like a short. So the output impedance, what will happen? It will sort of drop. Again, this is all in log scale. So when I say it's 0, it's 0 dB. Okay, I mean. So now let's look at the second case where I am trying to compensate the loop by putting a really large capacitor at the output. So which means I am considering a case, say, make some space here. So I am considering where a case where C0 is much greater than C1. So again, at low frequencies it's going to be small, right? Now we keep increasing frequencies. Which cap will start to act like short circuit first? C0. So what will happen to the output impedance now? It will start to drop. Now after some frequency, C1 will start to behave like a short, and we already know C1 introduces both a pole and a zero. We have an inductive component, so maybe it will do something like this. Right? We have a zero and a pole, first zero and the pole, right? So it is dropping, we encountered the zero. So now with respect to the output impedance, which of the two options is better? Seems like having a dominant pole compensation at the output is better. But of course, there are other considerations you might want to look at. I'll give one such thing as a practice set to work out. So again, you'll find some cases this is better, some cases this is better. It's all a trade-off. Okay, so now let me just mention one other considerations here. So with respect to LDOs, another important consideration is this. I want to, again, the idea is to keep this output voltage to be constant irrespective of any changes in the circuit. So which means even if I have a small signal disturbances on the supply here, my small signal change here should be what? 0. That's what I should expect. And this is called the power supply rejection ratio. I think we already. So let's briefly see what will happen. First, let's calculate what is the, if I call it V out. At DC without any capacitors, let's calculate what is V out. No cap. Right. So I have V in at the source. So what if I call this as V out? This point is beta times V out. So what is this voltage now? Oh sorry, actually I messed up. Signs are different. I'm really sorry. I think the signs are this way, right? Oh, I didn't change it, is it? Oh, completely sorry. Yeah, sorry. Signs are different, right? Because we already saw here. I thought I changed it, right? Or okay. Signs are inverted. Okay, I'm really sorry. Now, okay, because remember you also have an inversion here. So yeah, I thought we discussed it, but maybe I didn't change it. Sorry. Yeah. So what is the gate voltage here now? No, is it minus or plus? Yeah, plus GM R0 times beta. I'll call it as A1 times beta times V out. Okay. A1 is essentially GM R0. Okay. So what is the small signal current flowing here? I mean, let us say what is the current flowing in this direction? If I call it I0. Huh? No, look at the, yeah, okay, fine, yeah. V in minus A1 beta times V out. Let's, for simplicity, ignore R0 of the PMOS transistor so that we can quickly simplify it. So then what is my output now in terms of the current? I mean, I know the current I0. What is my output voltage now? I0 times K times R1. Okay. I mean, ignoring the R0 of the PMOS transistor, so you don't have to worry about this resistor. So if you simplify it, what do you get? K times R1. So this should be GM of the PMOS times K times R1 by 1 plus beta A1 times GMP times K times R1. So how can you approximate this as? Loop gain is really large, so what is this approximately? 1 by beta times here. Right, so once again, if you have sufficiently large gain from the first stage, any changes you see here, for DC at least it's suppressed. So which means in steady state, whatever change you make here will be suppressed. But of course now let's see with all capacitors how this will look like. We'll get a qualitative sketch. So this is the result at DC. I'll erase all this. Let me remember, this is the result at DC. So again, let's consider two cases. Let us say I am putting a dominant cap at the gate, or I have a dominant cap at the output. So let's first take this case. C1 is much greater than C0. Again, I am trying to sketch the PSRR versus frequency in dB. Okay. So now tell me again. Let's take at DC it's going to be a really small number, beta 1 by beta A1. I mean it's going to be a really small number, much smaller than 1. So if I take log, will it be positive or negative? Negative. So I'll probably, to avoid confusion, what can I do? I'll say negative of PSRR or something important. We look at positive stuff. So it is starting here. A very small number but positive. So it starts here. At DC we know. Now again, as I keep increasing frequency, what will happen first? C1 starts to behave like short circuit. Correct? So, oops. Yeah. Now this gate is incrementally short. So I am applying V in at the source. Gate is incrementally short. What kind of configuration is this now? Common gate. So I apply input at the source. So what will be the current now? Yeah, it's just see. So what will be the output now? GMP times K times R1. That will be, and this will be small number or a large number? It's going to be really large. GM times a resistor, and this resistor, remember, will typically very large, so that you want to reduce the current in the branch. So it's going to be really large. So once again, from a small value it goes to a large value. So once again you have a 0 on the pole. Again same thing, right? This capacitor once again contributes to 0 on the pole. And as you keep increasing frequency further, C0 acts like a short circuit. So now let's see if we can make this better. See, remember that as I keep increasing frequency, now I have problem, right? And the problem is happening because at sufficiently large frequencies, C1 is acting like a short circuit. And the moment C1 acts like a short circuit, the way I have wired up the circuit is such that the gate is incrementally shorted. Now remember, the entire loop is based on the premise that any change I see at any point is sort of suppressed by the loop by changing the gate voltage here. Correct? That's the whole principle. But now the way I have wired up the circuit is such that when the capacitor is acting like a short circuit, the gate is also shorted, it is not responding. Right? So, and remember, C1 is a cap that we are going and putting. So we have right now put a capacitor from this node to ground. Is there some suggestion that you can tell me by which, even if the capacitor acts like a short circuit, if I make any change at the source here, I should be able to get that change here? Because anytime I have a change, if the change is reflected to the gate, I am fine. That argument is clear? Huh? Resistor R from where? From where to where? But how will that solve the problem? You want to introduce a 0. From where to where? Okay. See, the idea is, I cannot prevent the fact that the capacitor will act like a short circuit at high frequencies. That is something we can't change. Now, it is us who have gone and put this capacitor from this node to ground. Which means if this is if capacitor acts like a short circuit, this node is shorted to ground. Now, what I am saying is, when the capacitor acts like a short circuit, I want the change in Vin to be coupled here, right? So instead of putting the capacitor to ground, I can connect it here. Because remember, for technically this is a supply VDD, that is also small signal ground typically. That makes sense? So now if you do this, let's quickly see what will happen, right? So maybe I'll choose a different color. Let us say I do this. Okay. So now at high frequencies, this is acting like a short circuit. So now what can you say about VGS 0? If VGS is 0, what can you say about the current? What will be the output? Ideally it is 0, but in practice you also have gate parasitic capacitor from this to ground. That is a parasitic capacitor of this MOSFET. So it won't be exactly 0, but yeah, I mean something will be there. So which means now the response will start from here, but then it will start to drop. And now you tell me, if I find that now I short the capacitor here, output is 0. So do I have a 0 in the circuit or not? I short a capacitor, but the output is 0, so there is no 0. So which means if I plot the characteristic, I will not encounter the 0. So it will basically do this, encounter this pole, and then it will sort of drop. So this is something that is common, right? Now similarly you can qualitatively plot and see what will be the PSRR if C0 is greater than C1. I'll give it as an exercise. So the point I want to make is this, I mean LDO or linear regulator is essentially a two-stage op-amp. So tomorrow if in your company if someone asks you to design LDO, you can't say that hey, this was not taught in my class. The same thing you learned for two-stage op-amp exactly holds good, just that the metrics of interest are different, right? So here you are interested more in the output impedance, PSRR and etc. But whatever you learned with respect to pole zeros, small signal will work. So to make this point, I usually show this following meme. It's like two-stage op-amp is like a normal Clark Kent. You put a nice cape and this looks like an LDO. And another meme is this. So it all looks like scary with a ghost LDO, but if you actually rip it off, it is just a two-stage OTA. So yeah, but so there are some fine prints, but at the heart of it, it is still a two-stage op. So I'll stop here. I mean, you can plot PSRR and it will all be negative. PSRR is less than 1 always, right?